Thank you so much for watching this online video tutorial. Like, comment, and share, as well as subscribe to our channel at Good Better Best Online Videos for more video content. Alright, grade 12s, welcome to the session today on redox reactions part 2. And of course, we're looking more specifically at the galvanic cell. Okay, should have been my heading, but don't worry, I can still add it in now. Okay, so we do have a very basic drawing of the galvanic cell, obviously with lots of labels, of course. We're going to go add in a few more labels, okay. We're going to add in a label here for the anode and cathode, okay. So we've got A for anode, and I didn't want to use C for cathode, so I used K, and C I rather use for the conducting wire, which is obviously the two electrodes, which are linked to the via conducting wire to the voltmeter, which is the electrodes are dipped into electrolyte solutions, of course, and a salt bridge, which allows, of course, cations to flow this direction, and of course anions, which are negative, to flow in that direction. Okay. Now, obviously, we know the anode, this is where oxidation occurs. Okay, so a bit of a tight squeeze in here, but oxidation occurs, of course, at the anode, and of course this electrode decrease in mass of this electrode, because obviously it starts to, when electrons are given off, the electrode starts to literally fade. Okay, but within the cathode, of course, a little bit different. Okay, cathode, obviously we know reduction takes place here at the cathode. Okay, and we add occurs in here, reduction occurs, and then this would now, because of the buildup of cations onto this electrode, this would obviously now be an increase in mass on this electrode. Okay, this is what happens, of course. Cations positive, all going to be collecting around the positive electrode, while the negative side is going to be losing mass. Okay. Okay. Electrolytes that will be used are different. Okay. In the anode, it's this saline solution with the corresponding ion as the anode. Okay. As well as with the cathode, it's also a saline solution with the corresponding ion as the cathode. For example, if the anode was a zinc electrode, there'd be a zinc sulfate electrolyte. If the cathode was a copper electrode, then the electrolyte would also be copper sulfate. Okay, so it's a salt solution that is basically made up of the corresponding ion of the electrode itself. So zinc with zinc, copper with copper, even though they're in electrolyte form. The definition of an electrolyte is it is a solution, or we could say it's a liquid. I like to use the first part. I like to use solution is a solution, liquid, or dissolved substance, which I've never used actually in any of my tests or exams. Okay, but more importantly, this part that conducts electricity through the movement of ions. I'm going to have to come down here, movement of, and I can fit it in here, ions. Okay, let's just scroll down here somewhere. Okay, cool. So that's what electrolyte means. So if the anode was a zinc electrode, a zinc anode, okay, or the anode or the electrode at the anode side was zinc, that was where oxidation was going to take place, then of course electrolyte would have to be a solution, saline solution, of course, with the corresponding ion as the anode, as the same thing goes for the cathode as well. Right, grade 12, just lend me your ears actually. We're going to need to figure out quickly how the cell actually works. Okay, so if you could just lend me your ears, we'll just explain a simple process, which is basically just more words than what you see on the screen. Okay, now electrons obviously released in the anode, okay, because that's where oxidation takes place. They are released, okay, and they flow through the external circuit, which is the salt bridge, okay, and they flow to the cathode, okay, where they are gained in the reduction half reaction. Okay, the salt bridge, of course, completes the circuit. Okay, so one of the functions of a salt bridge is that it completes the circuit. Okay, it's in basic, obviously you can see it's an upturned U-like shape, or literally, as some textbooks call it, a U-tube. Okay, with the letter U, not the word U, but the letter U tube. And of course, it contains some neutral solutions, so maybe some sodium nitrate, some potassium nitrate, or ammonium nitrate, or sodium sulfate. They cannot react with these others. They cannot react with other substances. Okay. Obviously, the ions, the positive ions, which are cations, they obviously flow through the salt bridge and they flow to the cathode. Well, anions, which are your negative ions, they obviously flow through to your anode, of course. That's basic sense. Okay. Thus, because of this whole process occurring, okay, we do say that the chemical potential energy, okay, so let's write it on top here, chemical potential energy. I know this is a pretty dark color. Is thus converted into electrical energy. Okay, now that's what I like to call pretty sweet, all right? Okay, pretty sweet. Okay, which is awesome. Okay, with an electrolytic cell, which is coming a little bit later, we'll see that the process is reverse. Okay, the electrical potential energy or electrical energy will be converted into chemical energy. Okay, but we'll get there a little bit later. Okay, cool. Now, just to touch on half reactions again. Okay, we all know that oxidation takes place at the anode now. But more specifically, the reducing agent donates electrons, and that would be oxidized. So if we had a look at the, just change back to a normal color, maybe green. If we looked at half reactions, and if we looked at them in general formula for the anode, okay, basically the half reaction for oxidation would be X, if that was the substance, is going to be, of course, X N plus the number of electrons and the electron symbol E. Okay, that's in the general formula. We just increase the brush size slightly. Then at the cathode, of course, it will be the opposite. So it will be, of course, let's use Y maybe. So Y N plus, because that shows that it's positive, plus the electrons showing that it's gaining electrons, would go to a neutral substance such as maybe like, I don't know, Y. Okay, that's the general. Okay, the anode, we can see, obtains a negative charge and would show a loss in mass, whilst the cathode would obtain a positive charge, and that would obviously show an increase in the mass. Okay, one of the most important parts here, this is examinable. I've seen it almost every year. Functions of the salt bridge, rather. Okay, let me just take A and put the there. All right, let's add it there. So first of all, there are three functions. The first function is that it separates the electrolytes. Because remember, you have two different types of electrolytes. You can't have the same. Okay, electrolytes so that they don't mix. You don't want them mixing with each other, because it has to correspond to this the anode or the cathode. The most memorable one because it's short, completes the circuit. But sometimes in a test, they might just pull a fast one on you and say, besides the fact that it completes the circuit, what is the other function of salt bridge? And then if you only bother to remember that one, well then obviously you're in a bit of trouble. Okay, so take time to remember all. The last one is that, also quite obvious, it supplies a path through which ions move, or ions can move. Okay, and you can just leave it at that, or you can go ahead and add the other part, which is which I'll put in brackets, to restore neutrality. Alright, so that's the functions of a salt bridge. It is examinable, so please make sure we do learn them. Alright. Cell notation grade 12s is basically a shortened way to represent the galvanic cell, and I haven't seen it much in papers though, since my time of school, which was about 8 years ago. This year is 8 years, so I'm approaching the big 10, round figure of 10 very soon, but I haven't really seen it much, but it is useful to know, just in case they throw it on you or they spring it on you like out of nowhere, like one of those people that dressed up as a bush and then they, like, you know, scare you very quick. Okay, so let's have a look at the form, or the general form in which it's written. Okay, so your reducing agent will be written first and will be separated by a straight line like this. Okay, of course you won't write it like this, I'm just writing underneath each other to save space, okay, which is called the cell terminals. Okay, and then on the other side you'd write your oxidized, I spelled that wrong, oxidized species, and then you'd have a double line in the middle. Okay, and then you'd have your oxidizing agent, separated by a line, and then you'd have your reduced species. Okay, so this obviously, this line here obviously is written to show one is obviously the anode and one is obviously the cathode. This in the middle here is the salt bridge. The double line shows the salt bridge. Okay, so if we have a example in blue, the reducing agent, which is obviously at the anode, this is the negative side, this is the positive side, would be Zn, solid. Okay, which is then my oxidized species, which would be Zn2 plus in aqueous solution, which is what happens, the zinc. And then you get the copper one, oxidizing agent would be Cu2 plus in aqueous solution, substance that gets reduced, and the reduced species, sorry, species, however you want to say it. Okay, I'm not going to bother with repeating the word all the time, I'm just going to sound more ridiculous. Okay, so what is it saying? Oh, and you got to put your negative and your positive side. Okay, so what is it saying here? The reducing agent is obviously showing the it's the part of the oxidation half reaction that is written obviously as such for zinc, which is Zn goes to Zn2 plus 2 electrons. Okay, so here's my reducing agent, and obviously my oxidized species, this is what it becomes after it's given up 2 electrons. And of course the oxidizing agent for the reduction half reaction, obviously it's written as Cu2 plus 2 electrons gives me Cu solid, which is not really even written in there because it's now reduced. it's gained electrons. Okay, so as you can see. Cool, so that's how it looks. Okay, that's called shorthand notation. Obviously this representing the anode, the negative, and this part representing the positive. So that's shorthand notation and can be written like this for almost any active cell. Right, what I want to go through next is called standard electrode potential or cell potential. Okay, now over here I pulled up a table of standard reduction potentials called table 4A, but there's also standard reduction potentials called table 4B. And I'm going to explain how to read these tables, read both of them. I think my favorite table was table 4B. I used table 4B the most. I think because I just understood it the best and it just made all the world of sense to me. Okay. But sorry, what? Can you repeat that, Abdulrahman? What you say?
What's the difference between table 4A and table 4B?
Okay, what's the difference between table 4A and table 4B? The main difference is that the one is written from one way down, as you can see here. This is not the only answer to this question I'll give. When I get to this part, I will obviously give a better answer. But you can see the one table starts with the positive numbers, written all the way down to the most negative. And table 4B starts with the most negative down to the most positive. Okay, so that's one of the most visible differences. So they're actually two of the same tables, just written differently, inverted around. But I will explain how to read both of them though, because basically it's almost like a bomber jacket that you can reverse and wear on both sides. It's the same jacket, two different colors, but it's the same jacket. Okay, but what I want you to pay attention to is the electrode potential values that you are given. You're given electrode potential values here. Okay, starts with, if you look at table 4A, starting with the positive, most positive, which could be the fluorine electrode. Okay, and it's the gas one, at positive 2,87 volts. Okay. Now, when a galvanic cell with two half cells is set up, obviously we know oxidation takes place at one and reduction takes place at the other. Okay. The tendency or potential of an electrode or an electrolyte to be reduced or oxidized determines which reaction takes place at that half cell. Okay. Now, potential difference forms between the negative electrode and the positive solution. Okay, that's why we call it electrode potential or half cell potential. So over here we have full of tables full of half reactions and their half cell potential. Okay, that's why we call it standard reduction potentials. Okay, similarly, a half cell potential or difference develops when the positive electrode and a negative electrode in the half cell where a reaction occurs. So in two of the electrolytes, in two of the anode and the cathode, two of the electrodes, there is potential differences happening there. Okay, and we denote it by the electrode potential, which is E with the theta sign. All right, is measured in volts. Okay, it's a numeric value. Okay, so if we have a look at an example here, let's take a look at silver, which is I think it's 0,8. Over here, I don't know if we can all see. I think it's a bit faint there. Let's just zoom in on the screen so I can see how small it is. I think that's big enough. Yes, so let's find it over here. This is silver Ag. Positive plus an electron gives us solid Ag. Okay, and that has an electrode potential of 0,80. Positive 0,80. Now, it's quite high up on this table. So what that means is when you're looking at cell potential or electrode potential on the tables, a large positive potential indicates that a substance will be reduced. Okay? Because it is a stronger oxidizing agent. Very important, you will see this term a lot, especially in your explanations, you'll be using them a lot. Why is silver, which is Ag plus an electron, tends to just solid Ag? Why is it considered to be, considered to be the reaction that takes place at the cathode? It's because it has a large positive electrode potential, meaning it's a stronger oxidizing agent. Okay? Similarly, the opposite is also true. Okay? What happens if I take a large negative? Okay? A large, and I'm just going to say a large negative. I'm going to write it in orange. Negative potential, or negative electrode potential, okay, indicates that the substance will be most likely reduced. Sorry, not reduced, oxidized. Okay, why would a large negative electrode potential indicate that a substance will be oxidized, or probably be oxidized? It is because it is a stronger reducing agent. Okay, like, for example, let's take the example lithium. Lithium becomes Li plus electron and has a electrode potential of minus 3,04 volts. It's quite a large negative electrode potential, so that's how we can tell that the substances now will most likely be oxidized. Especially if we had a lithium electrode and a silver electrode, we could definitely see there that based on one is positive and one is negative, one is quite largely positive and one is quite largely negative. The largely positive will mean, of course, it's going to be reduced, and the one that's largely negative, most likely to be oxidized. Now, the question that I've gotten many times in the past, and I'll probably have this question now as well, is, Japes, how do we know if we have two positive or two negative, which one is which? Okay, still the same principle applies. If we have two positive, the one which is more largely positive is going to be your reduction electrode potential. The one that's less largely or less positive, for example, 0,80 is larger than 0,25. Okay, so the one that's bigger, that's reduction. The one that's smaller, that is obviously oxidation. That's going to be oxidized. That's how it works with the positives. All right. The negative, though, if you have two negatives, the one that is most negative, remember, negative numbers increased further to the left and not to the right. Okay, so if we had minus 2,87 and minus 3,04, which is lithium, then lithium would still be oxidized, and minus 2,87 is larger than minus 3,04, so minus 2,87, that would be reduced. Okay, that's how we think about it, and that's how it's still, that same principle is still applied. Now, the formula for calculating electrode potential, cell potential, is given as follows. Okay, the electrode potential of the cell is equal to the electrode potential of the cathode, okay, minus the electrode potential of the anode. Always. Okay, this cell potential here is also called the EMF or potential difference. Okay. Cool. Now there are standard conditions though for these potentials to take place, and obviously we must know them because they could be asked, name the standard conditions for this to take place. Okay. The standard conditions. Alright. Number one, of course, the temperature, which I'm just going to shorten to temp, must be equal to 25 degrees Celsius. Number two, the pressure, which I'm going to write out full, is equal to 101.3 kilopascals. Okay? That's only if one electrode contains a gas. Okay? And the third condition is that concentrations must be equal to 1 mole per decimeter cubed. Okay, this is for your electrolytes only. Alright? Sweet. Sweet. I'm happy. Okay. Let's see. Alright, cool. I think we're good for now. They can go ahead and explain how those tables are written right now. Alright, great. So let's have a look at the table 4a quickly, which is also table 4a and table 4b form part of the table of standard reduction potentials. Okay, table 4a has a name specifically. It's actually the table of decreasing reduction potentials. The reason why it's called the table of decreasing reduction potentials is because if we go back to the table here, we actually have a look at it. Okay, we can see that it starts out on the most positive number of positive 2.87 and then goes all the way down to the most negative, which is minus 3.05. Okay, now on the table in the exam, going up, it says increasing oxidizing ability, and on the right hand side it says increasing reducing ability, okay, which I've labeled them slightly differently. Okay, going up the table is basically the reduction potential or the strength of the oxidizing agent, whilst coming down is the strength of the reduction or reducing agent, which is the oxidation potential. Okay, going down on table 4a. Okay, because going up, oxidizing ability, okay, of course, as we get up, which is the oxidizing agent ability, and coming down is the reducing agent ability. So going up, we are having more reduction. We're getting up to the more reduction side of the table, and going down, we're getting down to the more oxidation side of the table. Okay, but how you read the table is that if you read it from left to right, you are looking at the reduction half reaction. If you read it from left to right, table 4a, you are looking at the reduction half reaction. Okay, going up the table, of course, you're going and leading it at left to right. Okay, but if you're going to read 4a from right to left, you're going to be reading the oxidation half reaction. Ah, you spelled that right. That's how you read table 4a. Okay, thus the oxidizing agent or oxidation ability, okay, is going from the oxidizing agent will obviously works with reduction half reaction, so that is from left to right, and of course the reducing agent works from, of course, right to left. Okay, in a spontaneous redox reaction. For 4b, the opposite would be, of course, true. Okay, so I'm going to draw 4b quickly. We'll have a look at it. So table 4b, very similar. Okay, it's just now inverted. It's the inverse of table 4a. Okay, now going down table 4b, we have increasing oxidizing ability. Okay, and going up table 4b, we have increasing reducing ability. Okay, So the table is now read from the right to left. Now we are looking at the oxidation half reaction, and from left to right we are looking at the reduction half reaction, exactly like the same in table 4a. It's just now inverted. So I used both when I was in matric, because whenever I wanted to look for the oxidation, if I found the anode, I just looked at table 4b because it would help me look for the stuff on top. And then when I was looking for reduction, I used table 4a because it would also help me look for the stuff on top. Of course, you could use just one if you wished. I just used both because I understood both, and I was like, well, there's really no difference. It's the same values, it's the same type of reactions. The one is just inverted. Let's just go ahead and use both for the fun of it. Okay, so I did, and that was easy. Okay, so this is how you read the table. You can use both if you want, or you can choose to use one and just understand one fully and then just ride with it. Like I said, it's no problem. You shouldn't get confused between the two. Okay. And that grade 12 is all we're going to do for this evening session. Thank you so much for joining us and joining me today for Redox Reactions Part 2, looking at the galvanic cell. Next week we'll move on to the electrolytic cell, okay, and having a look at the processes that happens there and redox reactions in the electrolytic cell. Please don't forget to like, comment, and share, as well as subscribe to the YouTube channel, GBB, Good Better Best Online, for more online video content.